All right, so we have a 60 by 60 square here in the blue tape on the ground, and the robot is going to first drive around it with encoder values, and then we'll do a second time around with the IMU values, and we'll compare them. All right, so the first run will be just encoders. So we'll do our forward by counting the encoder counts, and then we'll turn by counting the encoder counts. So clearly not a perfect run. That can be due to the wheels slipping when we turn is probably the most likely thing. Small errors in heading compound. And then every time we miscount a turn, it adds to the error for the next turn. So let's see how the IMU does. So not a perfect run, but much better than the encoder run. We could see that every turn was approximately 90 degrees. Any overshoot was probably just due to the update rate of the IMU, but if we overshot one turn, the next turn was corrected because the IMU were going off of the heading based off our initial measurement, and that doesn't drift like the encoders do over time. The error doesn't add up, because if you're at 0 degrees and you turn to 90 and you actually accidentally turn to 92, and then you go from 92 and try to turn to 180, you already have accounted for that 2 degrees that you're already turned. So IMU seems to be much more reliable, which is what we expected. All right, so this is just a very brief high level of the code for the squares we just drew in encoders and with the IMU. So the initial pose when we start the run is 0, 0, 0 degrees. And then we have these functions that are encoder straight to drive straight for an encoder distance, where we're going to count the number of encoder ticks until we get to the distance that we want to get to. And then we have encoder pivot, which when we turn, we're going to count the encoder ticks until we get to that distance that we want. And then I want to highlight that the encoder pivot is probably where the most of our error is coming from, because we're doing skid steer. If a wheel slips and gets an extra encoder count, particularly with our robot, because we have 20 counts per wheel rotation, which means an extra tick can be a lot of distance, which results in a large heading offset. If we get a heading offset on the first turn, that will stack. So if we want to turn, let's say, right by 5 encoder ticks, and we turn by 6, well, now the next time we want to turn right, if we want to turn by another 5 encoder ticks, it's automatically going to have an extra encoder tick factored in there. So we'll be attempting to turn by 6 encoder ticks, according to our heading. The IMU fixes this because instead of counting the pivot every turn and just going by encoder ticks, if we jump down to the IMU pivot 2, we read the heading from the IMU, which when we first start the path, we set the heading to 0. We read the heading, and based on that, we decide if we've hit our desired turn or not. So if we turn 90 degrees to the right, like I was saying in the demonstration, and we turn 92, the next turn will know that our heading is 92 degrees already. So if we turn another 90 degrees to the right, we will stop at 180 instead of having those 2 degrees added to our path already. And that's why using the IMU to help specifically with turning, it makes our control much more reliable. Whereas those encoder ticks, it just takes a few, and that heading error will compound on us over time. So as one last note, we're just going to look at the paths that were recorded for the encoder only and the encoder plus IMU paths. So for the encoder only, because we're only using the encoders to track where we are, of course, it thinks that, as in the robot thinks, it has a perfect path. It thinks the first point, it starts pointing directly north. The second point, it turns exactly 90 degrees. And it's perfect all the way around because all it has to go off of is the encoder counts, and it's stopping at the correct encoder count. So it doesn't have any way to correct its data. Now the IMU path, it does show very small offsets by like a degree or a few degrees, but they're really hard to see visually because after the first turn, if it was off by a few degrees, it's not going to turn for a set number of encoder ticks for the second turn. It's going to turn until it's facing the desired direction, which is 180 degrees. So we don't have that compounding error to view. So it's interesting. The issue with the encoder only is we don't have enough data to show the error because we're not using the IMU. And then when we're running the encoder in the IMU, we're correcting for the error. So there's not enough error to show. So both of these paths visually look perfect.